Welcome back, everyone. Today we are going to explore the Ariane 6 launch system, the European Union's next-generation rocket designed to replace Ariane 5 and carry Europe's space ambitions beyond 2030. Understanding Ariane 6 requires looking at its origins, its technical structure, and the way it differs from both its predecessor and its international competitors. This video will take you through the design choices, the operational mechanisms, the supporting infrastructure, and the challenges that shape its role in the global space sector. By the end, you will have a clear picture of how Ariane 6 functions, why it was created, and where it is headed. The development of Ariane 6 was initiated by the European Space Agency and managed through ArianeGroup, a joint venture between Airbus and Safran. The program began as a response to rising global competition, particularly from SpaceX with its Vulcain 9 system, and to meet Europe's need for independent access to space. Ariane 5 had been highly reliable, but also very expensive. European governments and industries recognized that maintaining competitiveness required a launcher that was less costly, more adaptable, and capable of handling both commercial and institutional payloads. Ariane 6 was therefore designed from the start as a flexible launcher, with standardized components that could be produced more efficiently. Ariane 6 comes in two main configurations. The first is Ariane 62, which uses two solid rocket boosters attached to the central core stage. This version is tailored for medium payloads, such as smaller communications satellites or scientific missions. The second is Ariane 64, which uses four solid boosters and has a higher payload capacity suited for large commercial satellites and multiple payload launches. The modular nature of the design allows Ariane 6 to serve a broader market than Ariane 5, which had a fixed heavy-lift profile. This flexibility is central to Europe's strategy of competing globally. The core stage of Ariane 6 is powered by the Vulcain 2.1 engine, an upgraded version of the Vulcain 2 that powered Ariane 5. The Vulcain 2.1 burns liquid oxygen and liquid hydrogen, generating significant thrust to lift the central body. Its design improves manufacturing by simplifying components and lowering costs while maintaining high reliability. The upper stage uses the Vinci engine, which is also fueled by liquid hydrogen and liquid oxygen. Unlike Ariane 5's upper stage, Vinci can be restarted multiple times in orbit. This restart capability allows Ariane 6 to place satellites into different orbits during a single mission, and to perform complex maneuvers like deorbiting the stage after use to reduce space debris. The solid rocket boosters of Ariane 6 are designated P120C, with the C standing for commonality. These boosters are also used on the smaller Vega C launcher, creating economies of scale in manufacturing. Each P120C contains solid propellant cast into a large casing made of carbon fiber composites. When ignited, the propellant burns from the inside outward, producing enormous thrust to help lift the rocket off the pad. Solid boosters are simpler to operate than liquid-fueled engines, but they cannot be throttled or shut down once started. Their role is to provide raw initial power, while the liquid engines handle the sustained and controllable thrust. The Vinci upper stage engine deserves close examination. It is the first European upper stage engine designed for multiple restarts in space. This is achieved through its expander cycle design, which uses heat from the cryogenic propellants to power the turbopumps, rather than relying on separate gas generators. Restart capability allows for precise orbital insertion, especially important for constellations of satellites that must be placed into specific slots. For example, commercial operators launching batches of communications satellites can rely on Vinci to deploy each unit into the correct orbit without the need for satellites to carry large onboard propulsion systems. Ariane 6 is launched from the Guiana Space Center in Kourou, French Guiana. The site was chosen decades ago for its proximity to the equator, which provides a natural velocity boost thanks to Earth's rotation. For Ariane 6, a brand new launch complex called ELA-4 has been built. This includes the launch pad, flame trench, mobile gantry, and integration buildings. The mobile gantry allows the rocket to be assembled vertically in a protected environment before being rolled back shortly before launch. The facility also incorporates improved fueling and safety systems designed specifically for the Ariane 6 architecture. When comparing Ariane 6 to Ariane 5, the most striking differences are cost and adaptability. Ariane 5 was designed in the 1990s for heavy dual payload launches to geostationary transfer orbit. Its cost structure was acceptable at the time, but became less competitive as reusable rockets entered the market. Ariane 6 aims to cut launch costs by about 40% compared to Ariane 5. This is achieved through streamlined production, standardized components, and the shared use of boosters with Vega C. While Ariane 6 is not reusable, its design is intended to maximize cost efficiency within a traditional expendable model. One of the major questions surrounding Ariane 6 is reusability. Competitors like Vulcain 9 have demonstrated the economic and operational benefits of recovering and reusing booster stages. Ariane 6 does not attempt to reuse any of its components. Instead, European engineers are studying reusability for future projects, such as the Prometheus engine and the Themis reusable stage demonstrator. For now, Ariane 6 is positioned as a reliable, expendable launcher with reduced cost, while Europe continues to invest in research that could, hopefully, lead to reusable systems later in the decade. By 2026, it is expected that lessons from Ariane 6 operations will feed directly into these next-generation projects. Payload integration is another area where Ariane 6 differs from its predecessor. Ariane 6 introduces the payload-carrying structure known as the multiple launch system. This system allows several satellites to be stacked or clustered within the fairing, enabling rideshare missions that spread costs among multiple customers. For example, commercial operators launching satellites for Earth observation can share a mission with government institutions deploying scientific instruments. The flexibility of the payload adapters makes Ariane 6 more attractive to a diverse customer base. In terms of performance, Ariane 62 can carry about 10.3 metric tons to low Earth orbit and 4.5 tons to geostationary transfer orbit. Ariane 64 increases this to 20.6 tons to low Earth orbit and 11.5 tons to geostationary transfer orbit. These figures place Ariane 6 below Vulcain 9 in maximum capacity, but within a range suitable for most institutional and commercial missions. The key to its competitiveness lies not in raw lift capacity, but in offering European customers guaranteed access to space without reliance on foreign launch providers. Looking at near-term applications, Ariane 6 will be central to deploying Europe's Galileo navigation satellites, Earth observation satellites for the Copernicus program, and national defense payloads. In the commercial arena, it will support geostationary communications satellites and potentially small satellite constellations. The use of restartable upper stages and multiple payload adapters makes it particularly suited for missions requiring complex orbital logistics. As the market shifts toward constellations rather than single large satellites, Ariane 6 aims to remain relevant. Medium-term implications include Europe's strategic independence in space access. Without Ariane 6, European missions would rely heavily on American or private providers. The political and security risks of such dependence are significant. Ariane 6 ensures Europe retains its own launch capacity, supporting everything from scientific exploration to defense. Economically, the program sustains thousands of jobs across Europe in aerospace manufacturing, testing, and operations. It also supports regional expertise in cryogenic propulsion, composite materials, and systems integration that could be leveraged in future reusable designs. Long-term challenges remain. Ariane 6 is not reusable, and the pace of global innovation means that by 2032, expendable launchers may no longer be cost-effective. SpaceX and other companies are already moving toward fully reusable systems. To meet this challenge, Europe is testing Prometheus, a reusable methane engine, and Themis, a stage demonstrator that may evolve into a reusable vehicle. Ariane 6 thus represents both a stopgap and a foundation, bridging the gap between Ariane 5 and a future reusable European launcher. The technology developed and the experience gained will inform these next steps. Another limitation lies in the global launch market itself. Prices are being driven down by increased competition, and new entrants such as China's Long March 8 and India's GSLV Mach 3 upgrades will challenge Ariane 6 further. To stay competitive, Europe must continue to improve efficiency, secure institutional contracts, and develop advanced technologies. Even with its improvements, Ariane 6 might face difficulty winning purely commercial contracts against lower-cost reusable systems unless it demonstrates exceptional reliability and mission flexibility. One area of opportunity is the growth of satellite constellations for communications and Earth observation. These require frequent, reliable launches. Ariane 6, especially in its Ariane 64 configuration, can deliver multiple satellites in a single mission. By using its Vinci engine for multiple restarts, it can deploy satellites into precisely spaced orbital slots. This is a strong advantage for constellation operators who need predictable deployments. Case studies from upcoming missions will illustrate how effectively Ariane 6 performs in this role compared to Vulcain 9 rideshares or Russian Soyuz missions in the past. As we approach 2029, Ariane 6 will also be used in support of international partnerships. For example, it may launch components of the Lunar Gateway or scientific spacecraft heading toward deep space. The restartable upper stage makes it suitable for missions to geostationary orbit, medium Earth orbit, and even trajectories toward the Moon or interplanetary space. This versatility expands Europe's role in international exploration programs. By 2026, we should begin to see Ariane 6 missions supporting not only European projects, but also joint ventures with NASA, JAXA, and other agencies. In conclusion, Ariane 6 represents a major step forward in Europe's space capabilities. It combines upgraded engines, modular boosters, and a restartable upper stage to deliver more flexible and cost-efficient services than Ariane 5. While it does not embrace reusability, it serves as a platform that ensures independent access to space and provides valuable experience for the next generation of European launch systems. The rocket faces stiff competition and long-term challenges, but it is a necessary foundation for Europe's continued presence in space. Thank you very much for watching. Please like and subscribe.